Hi, welcome to part 6, I believe, of the series on Tellurium, our Python package for building and running simulations of biochemical networks. So in this video, I'm going to show you how you can change values and plot simulations based on those values that you change, and then you can observe how the dynamics of a system change as you change, say, parameter values. So this is the model we had before. Let me just run this just to show you what it looks like. So that's what it looks like. Remember, this is a closed system. Everything runs out eventually. So B runs to a maximum of 10, and A just runs out completely. All right, we have a linear sequence A to B, B to C, C to D. We start off with A is 10, and during the course of the simulation, the entire mass moves to D, okay, which is why D reaches 10. Okay. Now what I'd like to do is I'd like to study the dynamics of the system, say, if I changed K1. So if I changed K1 to 0.5, I'd like to know what happens to the dynamics. Now, in order to do that, I can just type in the Roadrunner object and dot, and then the name of the parameter I want to change, okay? And then I can just let's copy and paste this, then I can redo the simulation. All right. So I've got two simulations, one at where K1 is 0.1 and the other one K1 is 0.5. So let's run these two, see what happens. Now you probably didn't notice, but there was a flash there where two plots popped up one after the other. Let's look at the first one. This is the first one that came up. This came from line 22. The second one, however, came from line 26. So the first problem we have is they're two separate plots. Okay, maybe we could live with that. But the big problem here is that they look completely different. What's happening here is that the second simulation is basically starting off from the end point from the last simulation. So if you look at the last simulation, the end point for D, for example, is about 10. So if I look at the second simulation, you can see that it starts off at about 10. What I'd really like to do is for the second simulation to start at the original initial state. Well, there's an easy way to do that. You just ask it to reset the model. Just reset the model. If I reset the model, it resets A, B, C, and D back to their original values. Now if I run it, okay, there's the first one from line 22, and now this is the second one from line 27. And now you can see the dynamics are quite different. And that's because I increased K1 from 0.1 to 0.5. Now this is not really ideal either. What would be really nice if I could merge all the plots, then I could see what's happening maybe as I change a rate constant. So let's look at that. So I've got a pre-prepared model here. It looks a bit complicated, but we'll go over it. It's the same model as before, no change there. What I have added, I've added two imports. I'm importing NumPy, which is the array package, and I'm importing matplotlib. For NumPy, I'm only using one method called arange. And for the matplotlib, I'm only using two methods. The one thing to switch on the legend, and the one to just show the plot, just to finish off the plot and show it. So what does the arange do for NumPy? So let's pull that out. Let's put it into the console here. Let me clear the screen, and then let's do that. So let's run this. So this returns an array, and the array goes from 0.1 to 0.5. And these arguments in here basically indicate the start point, the end point, but not the actual end point. It'll be one just before the end point, and then the step. So the step is going in 0.1, starting at 0.1. So it should go 0.1, 0.2, 0.3, 0.4, 0.5, but it'll never reach 0.6. It stops at 0.5. If I could change it just to show you, let me change it. Go push it up to 0.9. Now you see it going from 0.1 to 0.8, one before the last value. If I wanted to go to 1, I need to put it at 1.1, but there's a slight rounding error here. I have to give it a slightly smaller value, and then it goes all the way from 0.1 to 1. Okay. So the other thing I can do, this is the starting number here. So let's go back to this one. Maybe I want to go from 0.5 to 0.7 steps of 0.1. Okay, there's a bit of a rounding error here I see as well. Well, let's take that back a little bit. Now it goes up to 0.7. Okay, it's doing a test on the last number to see if it's reached the end or not. And because of the rounding errors, presumably the 0.8 is slightly more than 0.8, which is why it's hitting 0.8 here. So I'm just giving it a slightly less number than 0.8. Then it takes me to 0.7. Okay, so this lets me then pick out multiple values basically pick out multiple values. And what I'm doing here is I'm having a loop here that will give me values in this variable I'm calling K1. It'll give me values 0.1, 0.2, 0.3, 0.4, and 0.5. And in this loop, I'll do a reset. We've seen that before. I set K1 to this K1. I then run a simulation. Now, I could plot all the curves, but that'll make a rather messy plot. So I'm actually doing a selection here. I'm going to ask for just time and the concentration of A. This is a little bit excessive. So I'm just asking for the concentration of A, so just one line. But then I'm doing this fancy thing here. So I'm using here a new plotting command, te plot array. This will take this takes a couple of arguments. One argument is m. You always have to give this argument. This is an array of columns, right? It's basically a series of columns of data. It'll treat the first column as the x axis and all subsequent columns as the y-axis. I'm then going to tell it, don't show me this plot. What it's going to do, it's going to accumulate the plots one by one, okay? And this is why when we come out, I do a show, and it shows that accumulated plot in one go. Actually, let me just run this just to show you what happens. I'm just going to show this little bit, and you'll see what happens. Okay, that's what you get. Now, notice first thing that all the colors are the same, and there's no legend. So that's because it resets the color spectrum or the color cycler every time, so it's always blue. So that's one thing we've got here, is to reset the color cycle to false. So that means it won't attempt to reset the color cycle, but it'll move on to the next color, the next color, the next color. If I do that, now I get lots of different colors, okay? The other thing, you notice here it's complaining that there are no labels found to create the legend because I'm asking it to make a legend. Well, I'm not giving it any labels. So that's what this last bit is for. I'm giving it a label. Let me just do this bit. I just do this bit here. Now, if I run this, of course, I get my legend, but I don't know what K is what. And that's why then I also add onto it the value of K1. I convert it into a string. This is the way in Python of converting numbers into strings, but I also format it so it only has 2 decimal places. Otherwise, I get far too many decimal places. Doesn't look good. So let's run this. And there you go. Now I get the legend showing me the actual values. In fact, let me just set this to 1 decimal place. I'll make it look even better. There you go. That's even better. So now I know that K1 is 0.1. When K1 is 0.1, I get the blue line. When K1 is 0.2, I get the orange line, and so on. And immediately I can see as I increase the rate constant, the system is the concentration of A is depleting faster and faster and faster. Now, of course, I'm not limited to A. I could look at B. Let's see what B does. That's what B does. That looks nice. I don't have to use K1. I could try K2. Let's change all these to K2. See what happens. Oops, it says K1 is not defined. See this error, K1 not defined? That's because I forgot to change that. K2, change that. Now run it, and now I get something like that. So you can see you can have a lot of fun with this to investigate how the different parameters affect the dynamics of the system. That's a pretty simple way, I guess, of it's basically doing a parameter scan, right? So you're scanning over a range of parameters to look at the dynamics. So just to show you You can go a bit crazy here. Let's do steps of 0.2, and you'll see what I mean. Okay, the legend has gone crazy. Let's turn off the legend. This is, of course, not a plot you'd actually do probably, but it does look very pretty. Okay, I think that's enough of that one. Okay, thanks a lot.